A bright field microscope is not just used for observing specimens and making qualitative observations. It's actually a very sophisticated measuring instrument. With a little practice, one can learn to measure the XY dimension of just about any object that you can see in a microscope. With a little more practice, you can measure vertical dimensions. You can estimate volumes, shapes, and sizes and so on of almost anything. You can also use it as a counting device. You can count concentrations of cells, for example, or beads in a suspension, or structures on the surface of a leaf. To use a microscope as a measuring instrument, there's a couple things we need to do. One of them is to, in our eyepiece, obtain a scale called a reticle, which enables you to measure linear dimensions. Now, the reticles don't come pre-calibrated, and in fact, the calibration, that is the distance that each division of a reticle represents, changes depending on the objective lens that we use. So for a given objective lens, we calibrate the reticle by using something called a stage micrometer. A stage micrometer is a ruler that's placed on a modified glass slide. It's usually a very thick slide. It may have a mirrored surface, or it may be a clear surface with etchings that are engraved and shaded. Whatever it is, the stage micrometer acts as a tiny, very, very accurately etched ruler, usually 2 millimeters wide, maybe 2.5 or so. And usually, because the calibration marks are so difficult to make precisely, and because the technique used to be very expensive, maybe it still is, one end and one end only will be etched to very, very fine markings. Typical stage micrometer would be about 2 millimeters wide. It would have divisions of a tenth of a millimeter distance per division, and then one end might be subdivided into increments of 0.02 millimeter, or maybe even 0.01 millimeter, 10 micrometers, which is pretty tiny. To use a stage micrometer, we can use it in a number of ways. We can use it to calibrate an eyepiece reticle. We can also use it to estimate field diameter. To use one, we place the micrometer on the microscope stage. Keep in mind now that because it's a much thicker piece of glass, the focal distance has to be a little larger. We have to lower the stage more than we would with a conventional slide. And we can focus on the scale. Now, once we're focused on the scale, one useful method of calibration is to calibrate the field diameter itself. With the field diameter estimated, we can estimate the surface area through which the light is coming, that is, the area of our field of view, and we can use the field diameter to count, say, the number of objects per unit area on a surface. It can even act as kind of a mini counting chamber, although we don't have a vertical dimension, we just have the XY plane. To estimate field diameter, we line up the stage micrometer so that one of the large divisions is at one side of the field, right on the edge. And then we make sure that the fine part of the scale, if there is one, overlaps the opposite side of the edge. We count the number of divisions, and then we can estimate the field diameter within some reasonable level of accuracy. In this case, we have 1, 2, 3, 4, 5 large divisions of 0.1 millimeter each. So we have a half a millimeter, and we have 1, 2, 3 fine divisions of 0.01 millimeter. That gives us a field diameter of 1, 2, 3. Make that 2 divisions, 0.52 millimeter total diameter. Now, from the diameter, we can then get our radius, which, of course, in this case is 0.26 millimeters. And then we use pi r squared to get the area in which we're viewing. Once we know the area, we can count objects that are seen in that particular field of view. This particular image is from what we call an epidermal impression. I took some Elmer's glue and smeared it on the undersurface of a Japanese privet leaf. Now, you could also do the same thing with nail polish that's usually used, clear nail polish, it takes nail polish longer to dry, and I think Elmer's does a perfectly good job. When you peel off the film and place it on a slide under a cover slip, you get impressions of the gas exchange organs and water vapor exchange organs called stomata. And it's useful in some studies to not only examine the stomata, but also to count them. When we count objects in a field of view, we set some criteria ahead of time. Once we know our surface area of the field of view, we can count the number in that particular surface area, and then get a number per unit area and report our counts in standard units, conventional units. But we do have to consider the case in which an object overlaps the edge of the field of view. Do you count it or not? When you're counting multiple fields, you can bias the count by undercounting or overcounting, depending on whether you choose to accept objects that overlap the edge or reject them. Standard practice when doing an unbiased count is to visually imagine the field of view as divided into 4 quadrants. What we do is we accept any object that overlaps the edge of the field of view in 2 of those quadrants, and we reject them in the other 2. I generally accept any object that overlaps the field of view if it's in the upper right quadrant, and I accept it if it's in the lower left. Reject any of those that are in the upper left, and reject any of those that are in the lower right. In this particular case, we counted 13 stomata in the field. There's actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15, I think, visible, but we rejected 2 of them. If one is to measure dimensions in the XY plane using the microscope, it's necessary to have some sort of a scale in the eyepiece or ocular itself. And we call such a scale an eyepiece reticle. The reticle can be turned in pretty much any direction by rotating the eyepiece, and the mechanical stage can be moved to line up any object and measure a dimension. But all reticles are not created equal. They vary in number of divisions and vary in number of divisions per unit length. The calibration of a reticle also varies with the objective lens that you're using. So as you change lenses, you change the calibration. What we do to calibrate an eyepiece reticle is to take our stage micrometer and use the mechanical controls to center up the scale so that it is superimposed underneath that the eyepiece reticle is superimposed over the micrometer scale. We then line up the divisions of the reticle with the divisions on the micrometer scale, line them up so that we can get a relationship between divisions on the reticle and divisions on the scale. In the example here, we were at 40 power, and the reticle is a 50 division reticle. It covered exactly 1 millimeter length of the stage micrometer. That gives us a calibration of 0.02 millimeters per division, which is the same as 20 micrometers per division. Now, if we change magnifications, let's say we go from 40 power all the way up to 400 power. If we do that, then the calibration changes in inverse proportion. So if we had 20 micrometers per division at 40 power, we're going to have 2 micrometers per division at 400 power. And likewise, if we were to go to 100 power or to go to 1,000 power, again, the calibration changes proportionally. But once you're calibrated at any particular magnification, you can just do the division or multiplication to get the calibration at any other magnification, even if you use a new objective lens, as long as you know the magnification of the lens itself. So we have our ocular micrometer here at 40 power that's lined up so that each division is 20 micrometers wide. Now let's see how we would go about measuring with it. Well, chances are your object, the dimension you're interested in, is not going to be lined up perfectly well with your eyepiece reticle. It's probably going to be turned. It might be off-center. We have limited control over the position of the specimen. We can move it around by manipulating the stage, but we can't rotate it. But we can rotate the eyepiece itself. And so what we do is we center up our specimen, and then we rotate the eyepiece until the scale crosses whatever dimension it is we want to measure. In the example of a spirogyra filament, we wanted to measure the diameter of the filament. I called it width, but it's really a diameter. Remember, we're working in three-dimensional space. Spirogyra is in the field at an angle, and we can't change that angle, but we can certainly position the cells, the filament, so that they're across the center of the field of view, and then we can rotate the ocular so that the reticle lines up perfectly well with the filament, and then count the number of divisions and get an estimate. 13 divisions, for example, at 20 micrometers division gives us a width of 260 micrometers. Now, when we resolve an object in the microscope and then we start to measure, we've got to remember that we can't be as precise as we might want to be. One of the studies that we do in my teaching laboratory is to measure the length of flagella in a unicellular alga, actually a protist, called Chlamydomonas. The flagella tend to be anywhere from maybe 10 to 15 micrometers long. And in my microscopes, when we view them at 400 power, that amounts to 4 or 5 divisions on my eyepiece reticle. Now, as I mentioned a while back, the maximum theoretical limit of a resolution of a light microscope, a bright field light microscope, is about 0.2 micrometers. And so you might be thinking, well, my goodness, we can measure to the nearest, probably 1/10 of a micrometer or so, right? Not really. The image here shows what flagella might really look like if a Chlamydomonas cell was blown up to the size that you see it. In reality, when we look in the microscope, the fuzzy image that you see here is about realistic. It's a lot smaller in the field. It doesn't look as fuzzy. But as a matter of fact, it's awfully difficult to tell if the flagellum is, 4 divisions or 5 divisions or 4.5. We're really not sure. And in my microscope, each division of my eyepiece reticle at 400 power spans 2.5 micrometers. If we estimate the length of a flagellum to the nearest micrometer, we're already somewhat overestimating precision. We have to take into consideration, then, when we report measurements, not only the accuracy of the scale itself, which is not as accurate as you might think, but we have to consider the resolution of the image itself as well. And we don't want to do things like report we saw 5 divisions with a scale of 1.25 micrometers per division, and therefore the average length is 6.25 micrometers. 1/100th of a micrometer is, in fact, 10 nanometers. Some atoms are 10 nanometers in diameter, and we certainly can't see them. On the other hand, if you report an average, then we do want to record full precision with each and every measurement. So if you count 4 divisions, multiply by the conversion factor, add your raw data up, take your average, and then after you've got the average, then we go ahead and suppress excess digits. I instruct my students to report the length of flagella to the nearest micrometer. That's fair enough. It overestimates precisions a little bit, but it's kind of difficult to round anymore. Now, not only can we measure dimensions in the XY plane, but we can measure the vertical dimension as well. It's trickier because you actually have to focus on different levels of the specimen. It's not always feasible, especially with very thin specimens. I happen to notice when I was examining this microscope and trying to calibrate my and measure depths of focus, I noticed marks on my fine control on the microscope. This microscope is actually calibrated so that each full turn of the fine focus knob moves the stage exactly 200 micrometers. That's really nice, and each division on this thing is 2 micrometers then. And so I could simply roll my fine focus, and I can count the divisions, and I can actually measure the distance traveled by the stage. If I was to go and look at a spirogyra filament or a paramecium, and I was able to focus at the very top of the cell and then at the very bottom, I could measure the distance the stage traveled and I can get a vertical dimension as well as getting the XY plane. And once you've got vertical dimensions and the XY dimensions, if you have a fairly regular shape, you can even estimate the volume. One thing you've got to be careful with, though, and that's why this sort of thing is tricky, is a phenomenon called hysteresis. If you move the fine focus in one direction and you stop at a particular point and you note the focus, and then you go past that direction and come back, rotate it in the other direction and come back to the same point, you should be in the same place. Chances are you won't be. Hysteresis is the principle by which the direction of change influences the final result. And with these fine movements, no matter how well engineered the focus rack is, hysteresis can make it very difficult to get very accurate measurements, particularly if you're moving in different directions, moving the stage up, moving the stage down. One thing I would recommend is if you're going to do a series of measurements this way, is to always start either below the specimen or always start above it and measure in the same direction each and every time. Now, when you're measuring depth, in this case I used difflugia as an example. A difflugia is a neat little protist. It's amoeboid-like, except this particular kind of amoeba builds a shell around itself called a test. The test has a remarkable structure to it, a very geometric kind of pattern. When you see these things, you're thinking, oh, it's just a spent shell or it's a hunk of sand or something. But then you'll notice a little movement. And if you focus very carefully and you have good contrast, you can see pseudopodia sneaking out from under the test. As you focus through the difflugia, enough light gets through it that you can actually see the aperture so that the shell has an opening in the base, and you can see the pseudopodia coming out from below attached to the slide. Well, this object has three dimensions, obviously. If you focus at the very top of the test, you can see the pattern. You would have to be at perhaps 400 magnification of 400 times to be able to do that, and the rest of it will be blurry. You know you're at the very top of the specimen. Now, if you raise your stage, you're working your way through the specimen, actually optically sectioning it, and if you get it up high enough at just the right point, you can see the aperture come into focus. Right through the shell, you can see the aperture. If you raise the stage a little more, you can get the very tips of the pseudopodia, which you know are touching the slide itself. You can measure the top all the way down to the bottom, measure the height of difflugia as it's sitting there on top of your slide, even though it's not visible in the XY plane. Another less tricky way to estimate depth, if you're good at math anyway, or arithmetic, is to simply record the volume of liquid that is placed underneath the cover slip. When you make a wet mount, what we do is put a drop of liquid, usually water, containing specimens, onto a slide, and we drop a cover slip on top. We might use a little film of Vaseline to hold the cover slip down into place. Suppose we put 90 microliters of water containing specimen on top of a slide, and we drop a cover slip on top that's 22 square millimeters, a square cover slip. The surface area of the cover slip is 440 square millimeters. We have 90 cubic millimeters of volume underneath the cover slip, and assuming it spreads out evenly then, the depth has got to be 90 cubic millimeters divided by 440 square millimeters, which gives us 0.91 millimeters in depth. We report that as 90 microliters because, after all, we don't have that kind of precision. You can use that mechanism or method, particularly if you have an object that you know is touching both the slide and the bottom of the cover slip. And as long as it's not pushing the cover slip up, you can get a very accurate estimate that way. When we need to count something, such as number of cells per unit volume, particularly with blood cells, we use what's something called a counting chamber. The most common type of counting chamber is actually called a Hemacytometer. It's so called because it was originally designed for counting red blood cells, white blood cells, and platelets. A Hemacytometer consists, like a stage micrometer, of a very thick slide, and it has mirrored surfaces on it, usually two, with little grooves. On either side of the mirrored surface are posts that hold a specially designed cover slip. The cover slip is typically 0.4 millimeters thick. Makes it heavy enough so it can compress any liquid that's on top of the mirrored surface, and it isn't pushed up or floated by the specimen that's underneath. The cover slip rests on a couple of posts so that there's a gap between the mirrored surface of the hemacytometer itself and the bottom of the cover slip. And that gap is quite accurate. It's generally 1/10 of a millimeter deep. So there's space underneath the cover slip there, and it's a calibrated depth. Now, on the mirrored surface of a hemacytometer is a grid. And the grid literally looks like this, very finely etched. The center part of the grid, you might note, superficially resembles a tic-tac-toe board. There are 9 big squares. Each of those squares is a square millimeter. So you might be thinking, aha, what we have is a calibrated surface area. We have a calibrated depth. If you put some liquid underneath the cover slip and count everything in that drop of liquid that happens to be under one of those large squares, you've counted all the materials that are within 1/10 of a cubic millimeter. What we can do, if we have very large cells, is count everything under each of, let's say, the 4 outside squares. Or we might, if we have smaller cells, we might count just within 1 square and do several counts of materials that are within 1/25 of a square millimeter. Or if we have very, very tiny cells, very densely populated, we might even go down to 1/400 of a square millimeter and count cells in some symmetrical arrangement of squares that is predetermined so we avoid bias. Here's an example of counting a cell suspension. The central square of the hemacytometer is the most finely divided of all. Each of the larger squares in that central square is 1/5 of a millimeter on a side. If we have moderately sized cells, we might count, let's say, the 4 outside corners in the central square. Rather than count them all, we don't want to count everything in there. We'd be there all day. We get a statistically significant count. By choosing a symmetrical pattern, we avoid bias, as we might get if we counted just a straight row or something of that sort. To get an accurate count, one with which we're fairly confident, we usually want to count somewhere between 1 and 200 cells. So if you count, let's say, 5 squares and you get a count of less than 50, then count 5 more. What we do then is we take the surface area under which we made our count. We take the depth underneath the cover slip, which is constant. And from that information and our count, we can go ahead and estimate a concentration of cells per unit volume. Now here's an example. As a preface to this example, let me say I took a suspension of cells that was very, very concentrated. When I first put it on a slide, it was so dense I couldn't see the individual cells. To be able to make it countable, I diluted it 100-fold by taking just 1 milliliter of cell suspension and adding 99 milliliters of buffer. Mixed it up very thoroughly, charged the hemacytometer by adding a little bit of liquid to the groove. And when we charge a hemacytometer, we put a little liquid in there and let it spread by capillary action underneath the cover slip. Just enough to cover the counting grid and no more. If we overfill the chamber, then we'll float the cover slip and we won't have an accurate depth. We won't get an accurate count. Now let's suppose we did count the 5 squares that I talked about in a symmetrical pattern, which is 1/5 then of a millimeter squared of area. And let's suppose and as an example, we counted 77 cells. All right, 77 cells in 1/5 of a square millimeter, 1/10 of a millimeter deep, gives us the following result. 77 divided by 0.2 square millimeters gives us 385 cells per square millimeter. Now, if we take that 385 and divide it by 0.1 millimeter, which is the depth of the slide, then we get 3,850 cells per cubic millimeter. And now we have a concentration. We have a number of cells per unit volume. Now, typically, we report concentrations of cells per milliliter. That's usually what's done. And there are 1,000 cubic millimeters in a milliliter. So we take our 3.85 times 10 to the third cells per cubic millimeter, and we multiply by 1,000 to give us 3.85 times 10 to the sixth cells, or 3,850,000 cells per cubic centimeter. Now that would be great, except we've got to remember that at the very beginning I diluted the original suspension by 100 times. So to get the count of cells in the original suspension, I've got to multiply back by the dilution factor. So we take our 3.85 times 10 to the sixth cells per milliliter, multiply by 100, and we wind up with 3.85 times 10 to the eighth cells per milliliter in the undiluted sample. That's how you use a hemacytometer. For other types of cell counts where they're more dense, less dense, larger or smaller, you simply adjust your measuring pattern. Knowing the measurements on the grid itself, you can get surface area, you know the depth, and you can go ahead and